All right, so for today, we're going to go over the 18 multiple choice questions from the Unit 8 review one by one. It's going to take a little bit of time, so we're going to kind of move fast through the easier ones and take a little bit more time on the harder ones. But with that said, let's go ahead and get started. Remember, this unit, the main focus of this unit were two things. Number one, L'Hopital's rule, and number two, the volume when you revolve around an axis, and the volume when you have perpendicular cross sections to a line. So we'll get into that. Number one, it says the limit as x approaches 0 of x squared over 1 minus cosine of x is. So remember, the first step in any limit is to try and substitute. So when we go to substitute in, we get 0 squared over 1 minus cosine of 0. And so we end up with 0 over 1 minus 1, which is 0 over 0. And we state, okay, if that's the case, that is an indeterminate form. Indeterminate form. And therefore we state L'Hopital's rule applies. Okay, L'Hopital's rule applies. You have to go through that sequence of justification. You have to substitute. If you get the form 0 over 0 or infinity over infinity, you state that's indeterminate, and then you state that you can now use L'Hopital's rule. If you don't get that form of 0 over 0 or infinity over infinity, then that means you have an answer. So your answer might be 0, it might be infinity, it might be just a specific number. That's fine. But you cannot use L'Hopital's rule unless you get this indeterminate form or infinity over infinity. So from here, remember, L'Hopital's rule said that the limit of a function is equal to the limit of the derivative of the top over the derivative of the bottom. So we're not using quotient rule here, we're just taking the derivative of the top, which is 2x, and then the derivative of the bottom would be sine of x, because remember, the derivative of cosine is negative sine, but we have a negative out front here. So now when I go to plug that in, we got 2 times 0 over sine of 0, and so we end up with 0 over 0 again. We go, oh no, what do we do? Well, we do L'Hopital's rule again. Again, that's indeterminate. Okay? And you can use L'Hopital's rule over and over and over again as long as you keep getting an indeterminate form. So then as a result, we get the limit as x approaches 0 of 2 over cosine of x. And then from there, we can say, okay, that's 2 over cosine of 0, which is 2 over 1, which is 2. So that gives our answer to be D. Okay? For number two, it's asking us to state which of these is true. So this one's pretty straightforward. There's no algebra to look at. It's just graphical. So we say, okay, the limit as x approaches a of f of x is equal to the limit as x approaches b of f of x. Well, if we look at the graph, we can see the limit as x approaches a from both sides, the limit from the left and the limit from the right, are both 2. Okay? But the limit as x approaches b is approaching two different values. So the limit from the left is coming in like this, the limit from the right is coming down like this. And since those two limits, the left-hand limit and the right-hand limit, are different, that means the limit as x approaches b does not exist. So the limit as x approaches a of f cannot equal the limit as x approaches b of f. B, it says the limit as x approaches a of f of x is 2. And that is true because we can see that the function is approaching the same value at this a value, okay? And that a value is in fact 2. Okay, so the limit from the left of a of f of x is equal to 2. The limit as x approaches a from the right is 2, and therefore we say the limit as x approaches a is 2. Okay, so that's number 2. Number 3, we have another limit expression, limit as x approaches 0 of sine of x times cosine of x all over x. This one's kind of a neat one because it uses some trig identities. You don't have to use them, but you can. If I plug in 0, again, substitution is always our first step. So we got sine of 0 times cosine of 0 over 0. Sine of 0 is 0, cosine of 0 is 1 over 0. This is 0 over 0. So what do we say? We say indeterminate form. So we apply L'Hopital's rule. Well, L'Hopital's rule, again, we want to say it, L'Hopital's rule is going to be the limit as x approaches 0 of the derivative of the top over the derivative of the bottom. Well, the derivative of the top is going to end up being a product. So we have to apply the product rule. The derivative of the first thing is cosine of x times the second thing, cosine of x, minus, let me put parentheses around this, minus the derivative of the second thing, which is negative sine of x, times the derivative of the first thing, which is sine of x, and then all over the derivative of the bottom, which is 1. So from here, we could just substitute and get an answer. It will actually work out just fine. But I want to point this out, that this is actually cosine x times cosine x is cosine squared x. And then the negative and the negative turn into a positive. And then we have sine squared x over 1, well, which is just, we'll just put cosine squared plus sine squared. And then you should be able to recognize this as a trig identity. So this is the limit as x approaches 0 of 1. Cosine squared plus sine squared is 1. And so the limit as x approaches 0 of 1 is just 1, because there's no x value to plug into. That's your answer. And so we end up with C as our answer there. Okay. One thing I do want to point out about indeterminate form, because I've seen a lot of mistakes, especially on one of the quizzes that we recently took. We had a problem, and I'll just give you a simple example here. The limit as x approaches, let's say 0 of 5 over x, of 5 over x. Okay, so we try substitution. We say, okay, substitution produces 5 over 0. Now here's where a lot of students get stuck. This is why they're getting lost. This is why they're getting it wrong. Students went straight from here and they said, oh, that's an indeterminate form. Therefore, L'Hopital's rule applies. No, because this isn't indeterminate. Okay? L'Hopital's rule only applies when you have 0 over 0 or infinity over infinity. This is neither one of those. Now, some of you will say, well, 5 over 0 is undefined. You're absolutely right. 5 over 0 is undefined. But it's not indeterminate. The word indeterminate means it cannot be determined by what we have here. Well, you have already determined that it's undefined. So you have an answer. But let's kind of go through real fast. This is wrong here, right? You can't use L'Hopital's rule. But if we go through a sequence of just logic, if I say 0 over any constant, 0 over any constant is 0 for the most part. There's one exception to that. If I say a constant over 0, any constant over 0 is undefined, but because we're taking limits, we're having x approach 0, we say that this goes off to either positive or negative infinity, and then we also say that it does not exist. Remember, there's two answers. When the limit is infinity, you also say it does not exist. So you have these things. Then you have another option. Infinity over some constant is infinity, and then some constant over infinity. As the denominator gets really, really big, the result ends up being really, really close to 0. Again, these are limits. These aren't the actual values, okay? We're saying as x approaches infinity, as x approaches 0 here. So all of these are valid answers. All of these are valid answers. None of these are indeterminate. In fact, we could go a step further and talk about another form. If I say 0 over infinity, you go, I don't know, that looks indeterminate to me because it just looks funny, it looks weird. It actually makes perfect sense. Watch what happens here. When I have a 0 in the numerator and I divide by any number, I should get a 0 out. Okay? The only exception to that is if I'm dividing by 0. We'll talk about that in a second. If I take 0 and divide it by any number, I get 0. So this top number is saying I should get 0 out. This thing on the bottom, the denominator, is saying infinity. Well, if I have any number divided by infinity, I should get 0 out. So this is telling me, this numerator is telling me my answer should be 0. The denominator is telling me my answer should be 0. They don't disagree with one another. They agree with one another completely. This answer is 0 because both the top and the bottom say the answer should be 0. Another example of this is infinity over 0. Well, if I have an infinity on top, I should get infinity out. And if I have a 0 on the bottom, then I should get infinity out. So the top thing is saying the answer should be infinity, and the bottom thing is saying the answer should be infinity. They agree with one another. Therefore, we can conclude that the answer is going to be plus or minus infinity, and then we'd also say it does not exist. The reason that we have to apply L'Hopital's rule is when we have a contradiction, when we have two things saying two different answers. And we can come up with lots of different examples. I can ask one person, hey, what is the best restaurant in town? And they would say, okay, the best restaurant in town is McDonald's, right? Yeah, right, but whatever. And then I can ask somebody else and I can say, what's the best restaurant in town? And they say, well, the best restaurant in town is Taco Bell. Well, at that point, they disagree with one another. And so the answer to which restaurant is the best in town is indeterminate based on the answers that I get, because these two people contradict themselves. But if I have one person say, hey, the best restaurant in town is Piology, and the other person says the best restaurant in town is Piology, well, those two people agree with one another, and therefore I don't have to really go much further. I can assume, based on that information, that the answer is Piology. Same thing here. These agree with one another. They both say 0, so the answer is 0. These agree with one another. They both say infinity, so the answer is infinity. The problem is when I get 0 over 0. You see, the top thing is saying that the answer should be 0. The bottom thing is saying the answer should be infinity. Those are two separate answers. They disagree with one another. So therefore, based on this information, that's when we say we have indeterminate. Okay? And then same thing here, when I have infinity over infinity. Well, the infinity on top says I should get infinity. The infinity on the bottom says I should get 0. Those are two different answers. They disagree with one another, and therefore we don't have a direct answer based on what we have in front of us. So we say indeterminate, and then we have to try some other method to find these limits. So I hope that clarifies some things for you. Hopefully you were paying attention to that, but we've got to move on here. We've got to fly. Number 4. Number 4 is saying the limit as h approaches 0 of the natural log of e plus h minus 1 over h. Now, our first thought in this is that, oh, we'll just plug in 0 for h and get an answer out. And we can try that. But the problem is if we look at all our answer choices are statements of fact. They're not numeric answers. And so just substituting a number in and getting a number out is going to give us nothing here. So what we have to recognize is that this is actually the definition of the derivative. So if you think about it, we would say f prime of x, going way back to unit 1, f prime of x, the derivative of f, sorry, unit 2, the derivative of f is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So that is the actual definition of the derivative. Okay, it is the slope as the distance between the 2 points approaches 0. Well, if we recognize that here, if we can identify the function that's producing this here, we can have a good feel for what this looks like. So the first thing we want to do is recognize what f of x is. Well, if this is the definition of derivative, we notice that the function is dictated by this first statement here, f of x plus h. Well, this says natural log of e plus h. Notice there's no variable there. But if I can put a variable there, then I would end up with the natural log of x. Okay? And we can check this. If I plug in the natural log of x for f of x here, this statement would say, f prime of x would say the limit as h approaches 0 of, natural log of x plus h minus natural log of x all over h. And so we can see that this is pretty close to this. The only difference now is that x is e and this natural log of x is 1. Well, if x is e, that means we're finding f prime of e. So if we test that, we plug in e to x, we get natural log of e plus h minus natural log of e all over h. And then we can simplify that a little bit. limit as h approaches 0 of the natural log of e plus h, and then minus the natural log of e is just 1, and then over h. And that's exactly what we had to begin with. So this statement is equivalent to f prime of e when f of x is equal to natural log of x. That's a little bit of a twist. We haven't done the definition of derivative in a while, but we have to recognize that so that we can plug things in and figure out from there. So the answer there was A. Okay. All right, number 5. Number 5, it says that f of x is equal to a piecewise function, where the first piece is the natural log of x, for 0 is less than x less than or equal to 2, and x squared natural log of 2 for 2 is less than x is less than or equal to 4. And we are looking for the limit as x approaches 2 of f of x. So remember, when we're looking for a limit, especially on a piecewise function, the first thing to do is substitute. The first thing we recognize is that we have a break in our piecewise at the point we're trying to find the limit. So we actually have to figure out the limit as x approaches 2 from both sides and see if they agree with each other. So the limit as x approaches 2 from the left is going to be using the top function, so that would be the natural log of 2. The limit as x approaches 2 from the right is going to be 2 squared natural log of 2, which is 4 natural log of 2. So we can see that the left-hand limit and the right-hand limit are not the same values, and therefore we can conclude, so these are not equal, we can therefore conclude that the limit as x approaches 2 of f of x does not exist. Because on one side we're approaching natural log of 2, and on the other side we're approaching 4 times the natural log of 2. So we have a jump discontinuity in number 5. So E is our answer there. For number 6, it says let R be the region between the graph y equals e to the negative 2x and the x-axis. For x is greater than or equal to 3. And we're looking for the area of the region R. So I'm going to go ahead and graph this. We have exponential decay here, so that is that function. And it says we're looking for the region that's bounded by the curve, the x-axis, and x is greater than 3. So let's call this x is 3. We are actually looking for the area of all of this. Now this gets really weird because if x is greater than 3, that means this guy is going to go on forever. But what I notice is that this function is actually approaching 0. Is it ever going to touch 0? No. And this is where students get really weirded out by this, because if it's never going to touch 0, then there's always going to be this thin little gap. So wouldn't the area be infinity? Well, we're not going to dive into that. The answer is no. This is actually a calculus 2 concept, but the approach to this problem would be exactly the same as we would take here. If I want to find the area in this region, we would just take an integral. So it would be the integral of e to the negative 2x dx, and now we have to figure out our bounds. Well, our lower bound is 3. Our upper bound, it goes on forever, so our upper bound is actually infinity. And so then we can evaluate this integral analytically here. We take the antiderivative. The antiderivative of this is negative 1/2 e to the negative 2x, and then we evaluate from 3 to infinity. Plug in our values, so we get negative 1/2 e to the negative 2 times infinity minus negative 1/2 e times to the negative 2 times 3. And then we simplify this. Notice that this is going to be a negative exponent, so e to the negative infinity here. Here we're going to get plus 1/2 e to the negative 6. If I move this negative exponent down, I'm going to get negative 1 over 2e to the infinity plus 1 over 2e to the 6th. Now, e to the infinity is infinity, and we just talked about this. E to the infinity times 2 is going to be infinity. And then as a result of that, because if we think of this as in terms of limits, because we're not actually hitting infinity, I guess you could say, negative 1 over infinity is 0, and then plus 2e to the 6th. So our answer is 1 over 2e to the 6th. Not asking you to fully understand the idea of infinity in integrals right now. It's a calculus 2 thing, but we can still solve this problem. So our answer here was A. Okay. Number 7. Number 7. It says the base of a solid is the region within the first quadrant enclosed by the curve y equals 2 rad 9 minus x squared. Okay, so the first thing I want to do before I go to solve this, I want to graph this. Now this is not a calculator problem, so it's going to be a little bit hard to see. What I recognize is that this looks similar to a circle because of the constant minus something squared. If I were to solve for the x and y intercepts, well, if I plug in 3 here, I'm going to get 0 out for y. And if I want 0 here, that would imply that, if I want 0 for x, if I plug in 0 for x, I'm going to get the square root of 9, which is 3 times 2 is 6. So we get this kind of curvy shape thing here, like an ellipse or something like that. Okay, so there is our function that we're looking at. And then it says the base of the solid is the region in this first quadrant. So the region we're talking about is just this part, and it's the base of a solid. So we're talking about finding volumes of cross-sections, of regions that are cross-sections of something, the x-axis and the y-axis. It says it has square cross-sections perpendicular to the y-axis. So we have square cross-sections perpendicular to the y-axis. So if I draw a line that's perpendicular to the y-axis, I can draw a square coming out of it, and that's kind of what we're getting here, a bunch of squares that are dictated by that distance. So remember, to find a volume of anything, the volume is always equal to the integral of the area function, or the area equation. Now, because we're talking about perpendicular to the y-axis, we have to put things in terms of y. So this will be the integral of a of y dy, and then our limits will be y values. So instead of slicing this way, we're slicing this way. And so we're going from 0 to 6 instead of 0 to 3. So now our next thing we have to do is get everything in terms of y. Well, up here, we have everything in terms of x. So we have to convert this first of all. So the first thing I'm going to do is divide by 2. So I get 1/2 y equals rad 9 minus x squared. And then I'll go ahead and square both sides. So I get 1 over 4 y squared equals 9 minus x squared. I'll subtract 9. So I got 1 over 4 y squared minus 9 equals negative x squared. I'll divide by negative 1. So I'm just going to flip these when I do that. So it'll be 9 minus 1/4 y squared equals x squared. And then square root both sides. So you end up with x equals radical 9 minus 1/4 y squared. And so there is our function or our equation in terms of y. But notice we need the area equation. This is just the length. This expression represents the distance from the y-axis to the curve. Now we need to figure out the area. So what we do is we draw a picture of the cross-section. It says that the cross-sections are squares. Well, we know that this length is radical 9 minus 1/4 y squared. Okay? And because this is a square, we know that all sides are congruent. So we can also say that this side is radical 9 minus 1/4 y squared. And so as a result, we can say our area equation is going to be rad 9 minus 1/4 y squared times radical 9 minus 1/4 y squared. And then we can actually simplify this to say radical 9 minus 1/4 y squared squared. And that cleans up nicely because the radical and the square cancel out. And so we're left with an area equation that says 9 minus 1/4 y squared. So there's my area equation. Now I just need to plug that into my volume expression. So we have the integral from 0 to 6 of 9 minus 1/4 y squared dy. And this is not a calculator problem, so we have to actually take the antiderivative. The antiderivative of 9 is 9y. The antiderivative of negative 1/4 y squared is going to be y cubed, and then negative 1 over 12 out front. And then that's all evaluated from 0 to 6. So that'll be 9 times 6 minus 1/12 times 6 cubed. And then subtract 9 times 0 minus 1/12 times 0 cubed. Well, that's all going to zero out, so that's okay. And then we can simplify this. So that'll be 54. And then minus, oh boy, 6 cubed. 6 times 6 is 36 times another 6. That's going to be 216. 216 over 12. And then I'll reduce that. Again, no calculators on this, so that'll be 108 over, 108 over 6, which is 54 over 3. I keep putting an equal sign there. And that'll be 54 minus 18. So 54 minus 18 is going to be 36 as our final answer, and that is correct. So our volume is 36, which means our answer is B. All right, so that wraps up the multiple choice questions that are non-calculator. Okay, so continuing on with the multiple choice questions that are the calculator problems. Number 8, it says that we are looking for the area that's enclosed by y equals rad x, and then y equals 6 minus 2x, and the x-axis. So if we go ahead and graph this, rad x looks like that. 6 minus 2x is going to have a y-intercept of 6 and a slope of negative 2. And we're looking for the region that's bounded by the curve, the line, and the x-axis, it says. So we're looking for this area. So what we need to do first is figure out where these two functions intersect. Now we have a calculator to do this, but we're going to show the work. We're going to say that they intersect when rad x equals 6 minus 2x. And we would type that into our y list. That would be y1, that would be y2. It would be a good idea to just start there anyways. And then we find the intersection using our intersection tool in the graphing component of our calculator. And we get an intersection of 2.25. We could have done that analytically, but we're not going to waste our time doing that. Now we notice that this region needs to be cut into two parts. We need to cut it into two parts. So one region is this part from 0 to 2.25, and the other region is from 2.25 to this point, which is our x-intercept. Our x-intercept here would be 3. So our equation for our area is going to be the integral from 0 to 2.25 of our radical function, dx, plus the integral from 2.25 to 3 of 6 minus 2x dx. Okay? And then from there, because it's a calculator problem, we're just going to plug that into our calculator. This first integral is 2.25. This second integral is 0.5625. And when I add that together, I get 2.8125, which is C. Now, we could have looked at this a different way. Instead of cross sections that are perpendicular to the x-axis, or instead of slicing it perpendicular to the x-axis, we could have sliced it perpendicular to the y-axis. And it would have actually made it just a little bit simpler in one regard, okay? In one regard. But to do that, we'd have to get these in terms of y. So to get this in terms of y, this would say x equals y squared. And then this, we would solve for that, so we'd end up with y minus 6 equals negative 2x. And then that turns into x equals negative 1/2 y plus 3. And if we look at it that way, where we're slicing it this direction, we can see that the line is completely to the right of the curve for this region. And so remember, to find the area of anything, it's the integral of the upper thing minus the lower thing. Because we're turning things on its side, it's the integral of the thing to the right minus the integral of the thing to the left. So it would be the integral of negative 1/2 y plus 3 minus y squared dy, because it's all in terms of y. And our bounds would be from 0 to whatever this height is. So this height is the y value of this intersection. So when you found your intersection here, it also gave you the y value, but we could go ahead and look at that and plug that in. 2.25, that's 4.5, so that would actually be 1.5 there. So we could evaluate this expression and we should get the same answer there. I'm not going to do that, but just as a side, we could do that. Okay. For number 9, it says, what is the area of the region enclosed by y equals 1 over 1 plus x squared and y equals x squared minus 1/3? Now some of you might be going, I don't know what that looks like, so how can I do this? Remember, this is a calculator problem. So if you graph both these functions, you'll see that the 1 over 1 plus x squared actually looks something like this. Sorry, that should be an even looking function. And then the x squared minus 1/3 looks something like this. Again, that should have a vertex of, or an axis symmetry of x equals 0. So we are looking for the area of the region bounded by those two curves. So what we have to do first is find their intersections. And so we will set those equations equal to each other. 1 over 1 plus x squared equals x squared minus 1/3. We're expressing the equation, we're writing the equation down, but we're not doing the work on our own. We're relying on our calculator to do that actual work. So we type that in y1, type that in y2, find the intersections. We actually get two intersections, and they are opposites. One is negative 0.932, and the other one is 0.932. And so when we set up the equation for the area, we would say area equals the integral from negative 0.932 to 0.932 of the upper curve minus the lower curve. So it's going to be of 1 over 1 plus x squared minus x squared minus 1/3. Do not forget your parentheses, and then dx. All right, keeping in mind that this is true as long as this first guy is always the upper curve, and in this case it is. So since this is always the upper curve and this is always the lower curve, this expression will be correct. If they change places and we're looking for more areas outside of that, or if a region is bounded by different things where these upper curves and lower curves change, you have to be careful on that. But in this case, we get an answer of 1.582, which is C. All right. For number 10, it says, what is the area of the region in the first quadrant enclosed by the graph of y equals cosine of x and y equals x? And so we can graph this, again, using your calculator. We're only concerned with the first quadrant, so we're going to graph cosine of x. Cosine of x looks something like that, and y equals x looks something like that. So we're looking for the region in the first quadrant enclosed by those two curves. Let's see here. Oh, and it says, and the y-axis. So we're talking about this region and the y-axis. So we're looking for this guy. So again, same concept. It's going to be the integral of the upper curve minus the lower curve. We have to find that intersection to figure it out. So we're going to set cosine of x equal to x and use our calculator to find the intersection of those two things. That intersection is 0.739. So the area would be the integral from 0 to 0.739 of cosine of x minus x dx. And we can get the antiderivative and all that, but again, calculator problem. So our answer, I believe it was like 0.399 something, 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 but when you rounded it to the 3 decimals, it was 0.400, which makes our answer C. All right. Number 11. Number 11, it says the base of a solid. Right here should be an indication that you're going to be finding the area of some cross-section. When you hear the base of a solid, okay? It says the base of a solid S is the region enclosed by the graph of y equals radical natural log of x the line x equals e, and the x-axis. And so if we type this into our calculator, we get a graph that looks something like this. This point is 1 because the natural log of 1 is 0. Okay? X equals e is somewhere over here, and the x-axis. So this is the region that is the base of a solid. Okay? And then it goes on, it says, if the cross sections of region S are perpendicular to the x-axis. So we're going to draw lines perpendicular to the x-axis. And it says that these cross sections are squares. So we can kind of have a square coming up out of it to visualize that a little bit. Remember that volume of any cross sections is equal to the integral of the area function. Well, we are going perpendicular to the x-axis, so this will be area in respect to x dx. Our bounds are going to be x's, so it's going to be from 1 to e. So the big question here is, what is my area? What is the shape I have? Well, I have squares. So let me go ahead and draw that square off to the side. I think this is very beneficial for us to see it. And we have to figure out the area of that square. Well, remember the area is length times width. The length is the distance from the x-axis up to the curve. And so that's dictated by the function itself. So this length is radical natural log of x. Because it's a square, this side will be radical natural log of x. And then the area will be radical natural log of x squared, because this times this. And that actually simplifies really nicely because the square root and the squared cancel out again. And so we end up with the volume equals the integral from 1 to e of natural log of x dx. Okay? And then we can use our calculator here. If this was a calculus 2 concept, then you could do this without a calculator. But this is a calculator problem for our sake. And so the result here is just 1, which is C. All right, that's number 11. Number 12. Whew, we're getting there. There's a lot of problems here. I get it. Number 12. The base of a solid is a region in the first quadrant bounded by the x-axis, the y-axis, and the line x plus 3y equals 9. And if you look, it actually gives us the graph here, and it gives us our x-intercept. So that makes it a little bit more convenient. It says that is the base of a solid, which means we're going to be talking about volume here. And it says that the cross sections of the solid are perpendicular to the y-axis this time, are perpendicular to the y-axis. So we're going this way. So before I go any further, I know that I need to take my equation and put it in terms of y. So x plus 3y equals 9. I need to solve for x because we're perpendicular to the y-axis. That's always the case. So we're going to solve for x. We get x equals 9 minus 3y. So this expression represents the distance from the y-axis to the curve there. And then it says the cross sections of the solid perpendicular to the y-axis are isosceles right triangles. Wow, this one's going to be a tough one. It says that they are isosceles right triangles where this is the hypotenuse. In the xy plane, this length is the hypotenuse. So let me go ahead and draw what we have here on its side. We have isosceles right triangles. We have let me do a little better job here. We have isosceles right triangles. So there's my right angle there. And it says that the length on the xy plane is the hypotenuse. And so we can see that this length here, this length, represented by 9 minus 3y, is the hypotenuse. And so remember, before we go to find the volume is the integral of the area function, and we're looking for area in terms of y here because we're perpendicular to the y-axis. And then our bounds are going to be from 0 to 3. And so there it is. We just got to figure out our area. Well, because this is a right isosceles, there's the right angle, there's the isosceles, we know that the area of a triangle is 1/2 base times height. Well, for me, the easiest way to look at this is to find this length and this length. Because they're perpendicular to each other, I can call those the base and the height. So I have to recognize this as a special right triangle. because this is a right isosceles triangle, we can use the parent triangle of the 45, 45, 90. Because if it's isosceles, and that's right, those both have to be 45s. Okay? And so if you remember, the parent lengths are 1, 1, and rad 2. So I'm going to call this side A, little a, and I'm going to solve for little a. So A, well actually let's do this. Let's call this B and H, base and height. So B, proportions, B over 1 is equal to 9 minus 3y over rad 2. And so we can cross multiply, but we don't need to because B over 1 is just B. So there we found our base. Now because this is a right isosceles triangle, the base and the height are going to be the same. And so we can say the area of the triangle is going to be 1/2 of this times itself, or 1/2 of 9 minus 3y over rad 2 squared. So that is the area of my triangle. I can now take that and plug it in up here because it's in terms of y. And so we end up with the integral from 0 to 3 of 1/2 of 9 minus 3y over rad 2 squared dy. That's a tough problem, okay? We have to get perpendicular to the y-axis, so we have to get in terms of y. We have to look at the right isosceles where that's the hypotenuse, so that makes it more difficult. If it said that this was the base, or if this was one of the legs of the right isosceles triangle, this would have been a lot easier to do, but we had to find these lengths using proportions here. And then we'll just plug that into our calculator and get our answer out. And so as a result here, we end up with 20.25, which is D. So that's a big, big problem. All right, if you thought number 12 was difficult, wait till we talk about number 13. 13 is talking about perpendicular cross sections that are equilateral triangles. So it says the region bounded by the graph y equals 2x minus x squared, the x-axis and the x-axis. So we have this graph and we have this parabola, and again we have a calculator to look at this, but our zeros are going to be 0 and 2 here, and the x-axis. So this region here is the base of the solid, okay? And from the base of that solid, it says each cross section is perpendicular to the x-axis. So because it's perpendicular to the x-axis, we need our equation in terms of x, and it already is, so that's good. That makes it a little easier. And it says for each solid, each cross section is perpendicular to the x-axis is an equilateral triangle. So before we even get into that, we can remember that volume is always equal to the integral from, in this case, 0 to 2, because we're perpendicular to the x-axis, of the area function, in this case respect to x, because we're perpendicular to x-axis, so a of x dx. So the question that we're going to have is, what is the area of our perpendicular cross sections? And it said that our perpendicular cross sections are equilateral triangles. Equilateral triangles. Since this length represents the base of this equilateral triangle, this length is expressed by 2x minus x squared, we can say that this is 2x minus x squared. So that's a good thing. Now, thinking about what the area of a triangle is 1/2 base times height. Well, we already have the base, so it's going to be 1/2 of 2x minus x squared. Now we need the height. And this is where this problem gets crazy, okay? We need the height. The height, remember, is the perpendicular height. So that's the height. How do we find the height? Well, we have to remember that this is also a special right triangle. If this is an equilateral triangle, all the angles in it are 60 degrees. So if that's a 60 and that's a 60, this whole thing up here is a 60, and we're cutting it in half. So now we have a 30, 60, 90 triangle. And so if we think of the parent lengths of a 30, 60, 90, opposite of the 30 is 1, opposite to the 90 is 2, and then the opposite 60 is rad 3. So we can set up this equation to find height using that. Now, one thing I'll notice, because 2x minus x squared is this whole length, it's not just this part. This length will be 2x minus x squared as well, because it's equilateral. So from there I can say h over rad 3 equals 2x minus x squared over 2. So that's just proportions back from geometry. And then we can solve for h by just multiplying by rad 3. So we get h equals rad 3 times 2x minus x squared all over 2. So that's my height. Because that's my height, I can plug it into my area function. So I got rad 3 times 2x minus x squared all over 2. And that is my area equation, which means I can plug it in to my integral expression. So I got the integral from 0 to 2 of 1/2 of 2x minus x squared times rad 3 of 2x minus x squared all over 2, and then dx. Get this out of the way here. Okay. So area of the triangle, 1/2 base times height. Okay. So there's your expression. You just got to plug that into your calculator very carefully. And if you did it right, you should be getting 0.462 out, which is D. To me, this is probably the hardest multiple choice question on this review. So I'm not asking you to memorize a formula here. I'm asking you to understand the concept. It's the volume is the integral of the area expression. And if it's perpendicular to the x-axis, it'll be a of x dx. If it's perpendicular to the y-axis, it'll be a of y dy. And then if you can draw one perpendicular cross-section, it said in this case equilateral triangles. Sometimes it'll say semicircles or squares or something else. If you can draw that and find the area of that expression or that shape, you can just plug that right into our volume expression. Okay. Number 14 is now dealing with revolutions. Revolutions are kind of cool. I like them at least. 14 says, what is the volume of the solid generated when the region bounded by the graph x equals rad y minus 2 and the line x equals 0 and y equals 5 is revolved around the y-axis? Now, to be able to graph this, to visually understand it, we can't type it into our calculator like this. So we'd have to solve for y. So we're going to go ahead and square both sides. We get x squared equals y minus 2. And then we'll add 2, so we end up with y equals x squared plus 2. So we actually have a parabola that is shifted up 2. Okay, let me draw that better. That was gross. Okay, we have a parabola that's shifted up 2. And we're looking for the region that's bounded by that, x equals 0, and y equals 5. And it says, let's see, line x equals 0 and y equals 5. So we are looking for this region bounded by those three things, and it says that it's going to be revolved around the y-axis. So if I revolve this around the y-axis, then we could say that this length here is my radius. Okay? And if you remember, just like all the cross-section stuff, the volume is always equal to the integral of the area. Well, in this case, because we're revolving, we're getting circles. So we're revolving around the y-axis, so we're going to talk about in terms of y. Our bounds are going to be from here to here. Our bound here is 2 because we have a shift up of 2, and 5 because the line y equals 5. And now we just need to figure out our area. Well, remember, area is equal to, in this case, because we're circles, it's going to be pi r squared. And so this length is my radius. So this equation, this expression here, represents my radius. So we can say, let me write this down, r equals rad y minus 2. And so when I plug that in here, I get pi times rad y minus 2 squared. And then if you think about the disk method, it's, remember, volume equals pi times the integral from 2 to 5 in this case of r squared dy. So either one of these expressions will work. This one will turn into integral from 2 to 5 of pi times rad y minus 2 squared dy. That's from that. Or we can just plug in our radius to our disk method. So it's pi times the integral from 2 to 5 of rad y minus 2 squared dy. But you can see that these are exactly the same thing. It's just that we took the pi as a constant out. This actually can simplify just a little bit because the rad y minus 2 squared So we can say pi times the integral from 2 to 5 of y minus 2 dy. That's my expression. And we'll type that into our calculator, which we wouldn't necessarily need to, but in this case we will, and we end up with 14.137, which is E. All right. So for 4 more problems left to go here. Number 15. 15 is a little interesting. It says, of 0 is less than or equal to k is less than or equal to pi over 2, the area under the curve of sine of x, there's sine of x, from x equals k to x equals pi over 2. Well, pi over 2 is right here. So we're looking for the area that's bounded by pi over 2 and k. Well, notice it says that k is between 0 and pi over 2. So that means k is somewhere in here. So this area is equal to 0.75, it says. So it says, let me reread it. It says the area under the curve of sine of x from k to pi over 2 is 0.75. And then we're looking for k. So to find the area of a region, that is just the integral, in this case from k to pi over 2, of the function, because we only have one function, so it's of sine of x dx, and it says that this is equal to 0.75. Now, we can't just type that into our calculator and get an answer out for k. We're going to have to do a little bit of work with our brains here. So remember, to take an integral, we have to take the antiderivative. So the antiderivative of sine is negative cosine of x, and then it would be evaluated from k to pi over 2, and that'll be equal to 0.75. All right, and then we'll plug in our upper bound, so it's negative cosine of pi over 2 minus negative cosine of k, and that's equal to 0.75. Cosine of pi over 2 is 0, so we get 0 here. This will turn into plus cosine of k, and that's equal to 0.75. So we get cosine of k equals 0.75, and to solve for k, we would take the arc cosine of 0.75, and as a result of that, we end up with 0.723, which is C. All right, so that's number 15. Number 16. Number 16, it says, what is the area of the region in the first quadrant enclosed by the graph y equals sine of x? So sine of x looks like this again. Y equals 2 minus x, so that means we're going to have an y-intercept of 2 and a slope of -1. And so it's going to look something like this. It's going to come down like that. So we're looking for the area in the first quadrant bounded by sine of x, y equals 2 minus x, and the x-axis. So we're looking for the area of this region right there. Okay. And then you can go ahead and use your calculator to graph that. I'm going to get rid of all these extra lines here so we can simplify this pretty easily. We have two options. We could put this in terms of y, and then this would be upper minus lower, or we can put it in terms of x, but then we'd have to split it at their intersection. I'm going to go ahead and do it that way. So the first thing we have to do is find the intersection. So the intersection is when sine of x equals, what was the equation here? It was 2 minus x. And then we'll type that into y1 and y2, find our intersections, and that intersection is 1.106. And so for this first region, the area would be the integral from 0 to 1.106 of sine of x dx. And for the second region, we would say plus the integral from 1.106 to whatever this x-intercept is. Well, the x-intercept would be 2. So to 2 of 2 minus x dx. Again, we can do the antiderivatives on our own, but it's a calculator problem. We end up with, for this integral, we end up with 0.552. And then for this integral, we end up with 0.400. And this is my rounded values. You should be using all the numbers expressed. Same thing for that intersection there. But as a result, we end up with 0.951 if you use all the correct numbers there, which is B. Okay. All right, that was number 16. For number 17, oh, here we go. It says the base of a solid. The base of a solid is the region enclosed by the graph y equals radical natural log of x minus 1, the line x equals 2e, and the x-axis. So if you graph this, you'll notice that this point is actually 2 because we have a natural log function that shifted to the right 1. And then 2e is going to be over here. And it says that this region is the base of a solid that's where the cross sections perpendicular to the x-axis are squares. So since we are perpendicular to the x-axis, we need it in terms of x. It already is. That's great. Remember to find the volume. The volume is always equal to the integral of the area function. This one's in respect to x. And then our bounds are going to be from 2 to 2e. And then we're going to look at our one singular cross section and determine that area. Well, the base of this square is going to be our function here. So that's going to be natural log of x minus 1. Because it's a square, that means the height's going to be the same thing, which means my area is going to be the natural log of x minus 1 squared. And so we can take that and just plug that in here. Volume equals the integral from 2 to 2e of natural log, sorry, it should be radical, and then here the radical, because we had radical there. So this will be, this can actually simplify then because it's a radical squared. This just becomes natural log of x minus 1. So we end up with natural log of x minus 1 dx, and then use our calculator to find that answer. We end up with 3.173, and our answer would then be B. All right, that's number 17. Number 18 is the last problem. Number 18. It says the base of a solid is the region in the first quadrant bounded by the y-axis, and the graph y equals arctangent of x, and the horizontal line y equals 3, and the vertical line x equals 1. So if you graph arctangent of x, it looks something like this. I think I'm going to need a little bit more room here. Okay. We're going to graph all of this stuff. That's arctangent in the first quadrant at least. And it says y equals 3. Y equals 3 is actually up here. X equals 1 is over here somewhere, let's say. And the y-axis, I believe it said. Let's see, yeah, bounded by the y-axis. So this region here is the base of the solid. And it says that the cross-section is perpendicular to the x-axis. So this length is perpendicular to the x-axis, are squares. So we're going to draw a square off to the side. This length represents the base of the square. Well, this height was 3, and this curve is the arctangent of x. So then this length is going to be 3 minus the arctangent of x. If you can see that, it's the upper curve minus the lower curve, 3 minus the arctangent of x. This side will be the same thing. And then the area of that equation is going to be 3 minus the arctangent of x squared. So therefore the volume, remember, is the integral of the area function, in this case in respect to x. Our bounds are going to be from 0 to 1, it said. And then we plug that in, the integral from 0 to 1 of 3 minus the arctangent of x squared dx. And then just type that into your calculator, and you end up with 6.612, which is B. All right, that was a lot of problems. I get it, I know, but hopefully that helped you in preparing for the next unit test. I hope you have a great day, and I can't wait to get back into class after all this coronavirus stuff.